Well, this is the 2018 paper for semester 8, question 3b. It's on the Poisson process. So it starts, the system of differential equations for the Poisson process is dp0 of t dt equals minus lambda p0 of t, and p0 of 0 equals 1. So this means that the probability of no events at time 0 is 1. That's fair enough. If we have no time, there'll be no events occurring in it. And that's the first equation. And the second equation is dpn of t dt equals lambda pn minus 1 of t minus pn of t, when n is greater or equal to 1, because if we say if n was 0, 0 minus 1, that wouldn't work there. And also that pn of 0 equals 0, that means the probability of 1 or 2 or more events occurring in 0 time is 0. Alright, so the question is outline the method of solution for this system of differential equations, which is the equation for the Poisson process. Pn of t equals lambda t to the n e to the minus lambda t over n factorial. Now there are 7 marks going for this question. 7 marks. Actually there's 6 marks going for this question, which means just over 7 minutes is what you can spend at it, really. So it's outline the method. You're not actually going to do the whole method rigorously. So if we have to get a solution, these here are first order differential equations. That means to get solutions we're going to have to integrate. So the first thing to know is that we must integrate in. Okay, we must integrate. And the first thing we do is we're going to do find p0 of t. Then we're going to find p1 of t. If we had time, we'd find p2 of t, and dot dot dot. But we mightn't get time for this. If we get this and show a pattern and lead into this here equation. Okay, so for the first part we're going to integrate dp0 of t dt equals minus lambda p0 of t. This type of integration you did last year, and this is called a separation of variables. Okay, you could imagine that p0 of t is like an x, and it could be dx dt equals minus lambda times x, you know. So, separation of variables. Type of integration. So if I bring the p0 across and divide, so it'll be 1 over p0 of t times dp0 of t dt equals minus lambda. Bring the dt up and we'll have 1 over p0 of t dp0 of t dt equals minus lambda times dt. Integrate both sides. And this here comes from, if we have the rule of logs, we have to integrate 1 over x dx. We'll get ln x plus c. We can leave the c to later. So if we integrate this, it's going to be the natural log of p0 of t. And that equals integrate lambda, and it'll be minus for there, lambda times t plus c. Now what we have to do is try to get the p0 of t out of the log. So if you imagine this is log to the base e, p0 of t equals minus lambda t plus c. Now the next rule we use is where you say, for example, you have log to the base 10 of 100, that equals 2. Say 10 squared equals 100. We're going to use this e to the power of all of that equals p0 of t. So we can write e to the power of minus lambda t plus c is equal to p0 of t. Then we'll use the e to the a plus b is the same as e to the a, e to the b, and split this up, and we'll have e to the minus lambda t, e to the c equals p0 of t. Then what we do is we use the initial conditions we were given. We use that p0 of 0 equals 1, so that means let t equals 0. If we let t equal 0, this equation now becomes e to the 0 times e to the c equals p0 of 0, which is 1. Right? So that's 1. Anything to the power of 0, say x to the power of 0 equals 1. So anything to the power of 0 equals 1. therefore c must equal 0, so we can have e to the 0 equals 1. And if c equals 0, we go back to the equation here, and we can say that p0 of t is equal to, that's gone, e to the minus lambda t. That is the first equation, okay? Now we still have to sort out the second equation. We'll use p1 of t next. So this is a much longer, but we'll have to do some shortcuts in this one, okay? So for this one, I'm going to let, this was the second equation given in the question, I'm going to let n equal 1. So we'll have dp1 of t dt equals lambda on 1 minus 1 is 0, p0 of t minus p1 of t. Okay, but we know what p0 of t is, we just found it there now. p0 of t equals e to the minus lambda t. So we can put this in, dp1 of t dt equals lambda times e to the minus lambda t, and multiply this out, minus lambda p1 of t. Right, we can rearrange this equation in the p1 of t over to this side, so we have dp1 of t dt plus lambda p1 of t equals lambda e to the minus lambda t. And this here now is ready for an integrating factor method of integration. Okay, so in this case the p1 of t would be like the y, if we have dy dt plus p times y equals q. So p here is the lambda and q is that, and y is the p1 of t. So we can say p equals lambda, q equals lambda e to the minus lambda t. These are for the integrating factor method. Okay, that means the integrating factor is equal to e to the integration of p dt. So that's going to be e to the lambda integral of lambda dt, which is equal to e to the lambda t. We'll leave the plus c till later. Right, so then if we multiply across by the integrating factor, we get e to the lambda t dp1 of t dt plus lambda e to the lambda t p1 of t equals lambda e to the minus lambda t times e to the lambda t, and they cancel each other out. So now we have e to the lambda t dp1 of t dt plus lambda e to the lambda t p1 of t, this one's bigger, equals lambda. Right, so now we're going to use what you call implicit differentiation, the idea of implicit differentiation. And basically if I was to differentiate lambda e to the lambda, no, if I was to differentiate e to the lambda t p1 of t with respect to t, I would get, if I differentiated, this is like u and v and a product rule. If I was to differentiate, so it's a u dv dt, right, that's e to the lambda t times d on dt p1 of t plus v p1 of t times du dt lambda e to the lambda t. And this here is the same as that. Okay, so that means instead of writing this down here, I can write this. So I can now say that d on dt of e to the lambda t p1 of t equals lambda. Now, for quickness, if you could remember, d on dt of yf, y times the integrating factor equals q times the integrating factor. This might help get through this bit a bit quicker. So that means now if I integrate both sides with respect to t, dt e to the lambda t p1 of t dt equals the integral of lambda dt. So that cancels, and on the left hand side we have e to the lambda t p1 of t equals lambda t. So P1 of t equals lambda t plus c, lambda t times e to the minus lambda t plus c times e to the minus lambda t. So now we have to go back to the original conditions, i.e. that P0 of 0 equal Pn, that should be an n there, Pn of 0 equals 0, i.e. the probability that n events will happen in no time is 0, right? So then we let t equal 0, that becomes P1 of 0 equals 0 plus c e to the 0. But P1 of 0 equals 0, therefore c must equal 0. So we finally have P1 of t equals lambda t e to the minus lambda t, right? And we had that P0 of t was equal to e to the minus lambda t. And then we could say that, because we're only doing an outline, that we could prove that P2 of t equals lambda t to the 2 times e to the minus lambda t over 2 factorial, and so on, getting that Pn of t equals lambda t to the n e to the minus lambda t over n factorial, and that's an outline of the method. Thank you.